So those are basic like molecular, but when it comes to the replication, at least, right? Yeah, we should know. Now let's take a step. Do you need a break? All right. So let's take a step forward. We've made DNA, but we know, right? We're in an imperfect world, which means replication cannot be perfect. No matter what we try, we have proofreading activity fine, but still there will still be some mistakes, right? Here and there. Not to talk of environmental factors that can what damage DNA, right? Yeah, sun exposure itself can damage DNA. UV light, radiation, other radiation can, ionizing radiation can damage DNA. So it's important to be able to know first of all the mechanism of damage. You have to know how those things damage DNA. Then you have to know how we repair, right, the damage. And then you also have to know what will be the consequence, right, if we cannot repair, right, the damage at this level. Yes, we have to know those things. Starting with a damage that we can see, right, as a result of a failure of proofreading from DNA replication itself, which is going to be mismatch, right, of nucleotides. Where I have A, I put C instead of T. Or where I have G, I put A instead of what? Instead of C. Mismatch. Nucleotide mismatch. So how do we repair mismatch? We have what? Mismatch repair, right? Proteins. And like example, MLH, MLS, PMS, whatever those things mean. Just know PMH, whatever. Yeah, those are the acronyms, right, of these proteins. So those are the mismatch, right? Repair. So M for mismatch, M for MLS, PMS. Yeah, they have some ME in there somewhere. Yeah. So those are the proteins, right, for mismatch repair. And when it comes to repair, right, there are three mechanisms of repair, three basic principles of repairing any damage in DNA. We will need to be able to sense the damage first. We must sense it, right? You have sensors. Then we have what? We have, I usually call it intermediaries. So there will be like a coordinator, like a conductor. A conductor can connect with the sensors. They will feed back to the conductor or the intermediate molecule, right, from the sensors. And intermediate molecules can what activate what the effectors. Those that will actually go and repair the damage. So you need to be able to send the sensors will send information to the what to the intermediate molecule, and then the intermediate molecule will now recruit the repairers or effectors and repair, right, the damage. So most of the time that intermediate molecule is what is P53. P53 is that intermediate molecule which can get feedback from the sensors. Those can scan DNA and sense the damage, and then P53 can recruit effectors that go and repair the damage. And if the damage is so severe that it cannot be repaired, PVG can also, well, it has a link to what? Programmed cell death proteins like BAX and BAC to trigger, right? Cell death. Yeah. So it's like a major player, right? In guarding the genome. So mismatch, MSH, blah, blah. So question, if there's failure of mismatch repair, what disease will that lead to? It leads to HMPCC, right? HMPCC. So failure of mismatch repair will lead to microsatellite instability. Basically, the genome becomes unstable, the chromosome becomes unstable because they have a lot of mismatches in there. And if those instability affect tumor suppressor genes or oncogenes, right, that can lead to what? Cancer, HMPC, so colon cancer. Also, there is for what? Reproductive tract, right? Cancer, endometrial cancer. ovarian cancer, right? Yeah, HNPCC. So a patient comes in, they have family history of multiple cancers across multiple generations. Yep, likely HNPCC. Mhm. All right. Sun UV light, ultraviolet radiation. How does that damage DNA? Mhm. UV is different from ionizing radiation. So how does it damage DNA? Exactly. And please don't confuse ionizing radiation from ultraviolet radiation. Right, they do different things to DNA. They are both of types of radiation, X-rays and rays or whatever, but they work differently. They do different things on DNA. UV radiation, so double-stranded or single-stranded DNA breaks. Any sort of DNA break will be what the ionizing radiation, right, which includes X-rays, CT scan, and radioactive molecules. Yeah, but if it's ultraviolet radiation, it's going to be pyrimidine dimers. Doesn't cause strand breaks. It causes dimerization of adjacent, right, pyrimidine of adjacent thymine, right? Thymidine dimers, right? Or thymine dimers, pyrimidine dimers. Yeah, that's what it causes. Good. So and for that one, that's what we have with the nucleotide excision repair, right? Yeah, repair system. So once that pyrimidine dimers are sensed or seen in the skin cells, keratinocytes, then we bring in exonucleases, endonucleases rather, remove the dimers, and then DNA polymerase comes in and replaces, right, the removed segment, right, with the appropriate, right, yeah, nucleotides, yeah, all right. So that's that. If that process fails, there's no repair of pyrimidine dimers. The pyrimidine dimers accumulate. What will be the consequence? It's going to lead to okay. Now, it's going to lead to skin cancer. Now, let's say somebody is born with a mutation, right, in those genes, in the nucleotide excision repair genes. Then that's what called xeroderma, right? Pigmentosa. But even people that don't have genetic mutation or hereditary mutation, as we grow older, right, what happens? We accumulate all these mutations, right, over time. That's why sun exposure, right, is a risk factor for what? Skin cancers. So even in the sporadic melanomas, sporadic squamous cell carcinoma, sporadic basal cell carcinomas, yeah, it's still gonna be they're gonna accumulate, right? Pyrimidine dimers in the skin in those cells. That's why they develop those cancers. So yeah, so having those periodontitis will lead to skin cancer. If the mutation in the if the patient accumulates the mutations because of hereditary mutation in the nucleotide excision repair system or genes, then that's what we call xeroderma pigmentosum. But at a very very young age, they are sun sensitive. They have dry skin, a lot of skin lesions, blisters, as well as their risk of skin cancer is about 2,000 fold, right? Higher than healthy people. Yeah. But don't also forget that sporadic cases too of skin cancers, right, will be due to accumulation of what? Pyrimidine dimers. Yes. Yeah. So that molecules like carcinogens, like nitrite, smoking, carcinogens in smoke, cigarette smoking, they can change the base in nucleotide. They're going to change just base. They are not damaging the whole nucleotide, just the base in the nucleotide. So they can cause what we call deamination. For instance, convert cytosine, right, to uracil, convert adenosine to hypoxanthine, oxanthine, convert guanosine or guanine rather to hypoxanthine. So basically they deaminase, remove an amino group or a imine group from all those normal bases we're going to see in DNA and convert them to like uracil, cytosine to uracil, convert adenosine to xanthine, convert guanine to hypoxanthine, right? By deamination. So carcinogens can do that. So the mechanism that will repair, right? That is what we call the base excision, right? Repair. Now, base excision repair. Base excision repair. That's how we repair changes in the bases of DNA. Any mutation that changes the bases in DNA. And that process involves also sensing, right? So each uh, base that we're going to be changing to is what? We have sensors, special sensors, like for each of them. There are sensors that can sense uracil. If there's uracil in DNA, right? There are sensors that can pick it up. If there's xanthine in DNA, which should not be there, there are sensors that can pick it up. If there's hypoxanthine, there are sensors that can pick it up. So each of them have specific sensors. We call those sensors glycosylases or glycosylase, like enzymes that they are glycosylase, specific glycosylase enzymes. So they can sense, if they sense uracil, they can remove uracil, uracil glycosylase. You can see it and remove uracil from that nucleotide. If xanthine glycosylase, if you see xanthine, is going to remove it. Hypoxanthine glycosylase, if you see, it's going to remove it. Yeah. So glycosylases. Once they see and remove those bases, then endonuclease will come in. Endonucleases will come in and remove the nucleotide, the whole nucleotide at that location. And then DNA polymerase will come in and replace, right? Put in the correct nucleotide. You said? Yeah, glycosylase, endonuclease, right? And then you have DNA polymerase and then ligase. Yeah, help for ligase, right? Ligase will join the fragments together. Yeah, that's base excision, right? Failure of that will lead to it can lead to a lot of cancers, especially gastric cancer, esophageal cancers, gastric cancers, because nitrates in smoked food or food preservatives, right, is a major cause of those mutations in the bases in DNA. Yeah, so if they are not repaired, right, patient will be at risk for right, esophageal cancer, oral cancer, gastric cancer. Yeah, will be a consequence of those. How do we repair single strand breaks? Single and double strand breaks. How do we repair that? You can join the remaining strands right together. If there's a break in DNA, you can just join them. Join the remaining strands. We call that non-homologous, right? Hand joining. Yeah, just join them. What is the problem with that? The problem with that is any piece of DNA that is lost during the break is lost forever, right? Because during the break, if a piece of DNA is lost, but I just take the remaining strand and just join them together, that gap or the piece that is lost from the gap left initially, right, is gone forever. So that is not efficient because it can introduce what? Deletional mutation, right, in DNA molecule, which can lead to cancer. Right, non-homologous end joining, yeah. On the other hand, we have homologous, right, repair. If there's this strand break, either double or single strand break, we can repair that break, right, through homologous repair. What that means is, remember that we have two copies of every gene, one from the father, one from the mother, and we call those homologous, right, chromosomes, homologous genes, right, basically, right, because they are exactly the same, except there will be slight differences, right? Yeah, but they are almost exactly the same. Chromosome 1 from the father is like almost the same as chromosome 1 from the mother, same genes, same sequences, but there will be slight differences, right? Yeah, polymorphisms. So we call if there's a double strand break or single strand break in one copy of a gene, what will I do? I can use the homolog, the other copy from the other parent, right, as a template to synthesize, right, to resynthesize the lost piece, right, of DNA, right, from the broken strand. Yeah. So in homologous repair, right, we are not losing any part of the DNA, right? We're not losing it because we're replacing it. We're going to replace it. We're going to resynthesize it using the homolog as a template. That's homologous repair. So it's way better than what non-homologous end joining. But in non-homologous end joining, you're losing the piece of DNA. In homologous, you're gonna resynthesize the DNA that was lost in the broken strand, so we're not losing any piece of DNA, right? And we can restore the DNA back to its what? Yeah, to its former glory. So the risk of things like mutation, cancer, right, will be low in that case. Um, Examples of genes that play a role. Okay, so causes of double strand breaks first, ionizing radiation. And how do ionizing radiations damage DNA? They generate what? Free radicals, right? Ionizing radiation damages DNA by generating free radicals. It's going to turn water into hydroxyl or reactive oxygen species, yeah, and right, damage DNA. All right, next, genes, right? So IU genes that we should know that play a role in double strand breaks or DNA strand break repair. For homologous repair, BRCA gene, right? Yeah, that's what BRCA gene does. Homologous repair. BRCA gene, breast cancer gene, right, is a tumor suppressor gene that plays a role in double strand breaks or even single strand breaks using what? Homologous repair. And that is why if BRCA gene is mutated, right, what happens in the breast tissue and the ovaries? Those breaks will accumulate. And when they affect what? Tumor suppressor genes, proto-oncogenes and co, they can lead to what? Breast cancer and ovarian cancer, right? Respectively. Yeah. A gene that plays a role in non-homologous end joining is what? ATM gene, right? Ataxia, right? Telangiectasia gene. ATM gene. It turns out, right, that non-homologous repair end joining, right? Non-homologous end joining is also used for what? for uh, immunoglobulin for recombination, right? Gene recombination in B cells. So remember antibodies, right? We have different segments of antibodies. We have the FC region, FAB region, we have IgM, IgG, So we have the light chains, heavy chains, constant region, variable region. We have the VDL, right? VDJ rather, J region, etc. So all those regions have genes, right? In B cells. So how do you recombine different genes, different V's, different D's, different J's, different heavy chains, different light chains, right, to form different types, right, of immunoglobulins is through that end joining. It plays a role in that recombination, right, of immunoglobulin genes. And that is why in ataxia telangiectasia, where ATM is mutated, in addition to having problem with the neurons, telangiectasia, ataxia, they also have problem with what? They accumulate mutation, right? In actually blood cells and they risk for cancer. Yep. Blood cancers, leukemia and stuff. And they're also gonna be what? At risk for recurrent infection because they are immunocompromised. B cells cannot make a lot of antibodies. Yeah, no recombination. So they're at risk for recurrent infection because of that. So that we should know. All right. So that's repair, right? Um, repair. Oh yeah, trinucleotide, right? Oh yes. Disorders that are due to trinucleotide repeats. Huntington, right? Um, yeah. Remember that those nucleotide repeats expand, right? It expands. They can expand, right? Where the mutation gets worse, or sometimes they present earlier in age, what we call anticipation, like in Huntington. Yeah. How do you think those things accumulate? It has to do with what mismatch repair problem. Yes. Has to do with defective mismatch repair. Because during spermatogenesis in Huntington, or during oogenesis, I've forgotten which one is related to oogenesis. I think it's myotonic, no, Friedrich ataxia or something, one of them, or is it Fragile X? Fragile X, right. So during oogenesis in Fragile X, or during spermatogenesis in Huntington, when there's a mistake, right? There's a nucleotide mismatch, and it's not repaired. If the mismatch occurs at the level of a trinucleotide repeat, right, it can lead to expansion of the repeats. So the mutation gets worse. And it's going to be passed on to what? To the next generation. So the next generation will have what? Worse presentation of the disease and earlier disease onset, right, than the previous, right, generation, than their father or mother. Yeah. So, right. Oh. All right. So that's DNA, right? 1 hour 30 minutes on DNA. That's that's a high yield molecule, right? Yeah, yeah. That's DNA, the, the unit of life. Okay, so we've replicated DNA, blah blah blah. Talked about DNA